Welcome to The Explainer. I am absolutely thrilled you're joining us today because, wow, we are diving into a molecule that is literally reshaping modern medicine as we know it. We're going to explore the fascinating science behind a single peptide that has just completely taken the global medical community and honestly, pop culture by storm. You know, you've heard the brand names, you've seen all the wild headlines, but today we're actually going to look under the hood at the mechanics of how this whole thing works.
Okay, let's dive into this. How exactly did a medication that was initially designed just to help patients manage type 2 diabetes unexpectedly evolve into this massive global weight loss phenomenon? And now, potentially, a groundbreaking treatment for severe addiction, right? It's wild. To understand this mystery, we really have to strip away all the marketing hype and look directly at the underlying biology.
First off, let's clear up a massive amount of public confusion. We constantly hear names like Ozempic, Wegovy, and Rybelsus kind of tossed around and used interchangeably, right? But they are actually entirely different brands with different FDI indications and delivery methods. So Ozempic is a weekly injection for type 2 diabetes and reducing cardiovascular risk. Wegovy, that's a weekly injection specifically dosed for chronic weight management. And then you have Rybelsus, which is a daily oral tablet for type 2 diabetes. But here's the crazy secret. They are all the exact same underlying drug. Yep, the whole shebang is just semaglutide.
So what exactly is semaglutide? Well, it's a synthetic version of something our bodies already make naturally, called GLP-1, which stands for glucagon-like peptide 1. Basically, it's a naturally occurring hormone secreted by your intestines right after you eat a meal. Its natural job is to tell your pancreas, hey, get ready to handle some sugar, and to tell your brain that, you're getting full. It's essentially the body's master regulator of glucose and appetite. But there's a massive biological problem if we actually want to use natural GLP-1 as a medicine. 2 minutes, literally just 2 minutes. That is the entire lifespan of natural GLP-1 in your bloodstream. You see, your body produces this enzyme called DPP-4, and it operates kind of like a microscopic shredder. It destroys the GLP-1 hormone almost as soon as it's released. So obviously, you can't treat a chronic disease with a drug that vanishes in exactly 120 seconds.
To solve this 2-minute problem, pharmaceutical scientists had to get creative. They engineered this brilliant suite of molecular armor for the GLP-1 peptide. It's like a tiny chemical spacesuit. First, they swapped out a single amino acid to physically block that shredder enzyme from cutting the molecule. Then, they attached a flexible spacer. And finally, to that spacer, they attached a very specific fatty diacid. And honestly, this fatty acid is the real secret weapon of semaglutide's longevity.
That fatty acid acts like a molecular magnet for albumin, which is the most common protein floating around in your blood. By binding super tightly to albumin, the semaglutide molecule basically hitches a ride and completely hides from your body's filtration system. This creates what's known in the biz as the depot effect. And the payoff of this incredible chemical engineering? The drug's lifespan in your body gets extended from a mere 2 minutes to an astonishing 168 hours. That's a full week. And that right there is exactly why Ozempic and Wegovy only require 1 injection every 7 days.
Now, what's really interesting about this slide is how scientists managed to put this peptide into a pill form, which is Rybelsus. Peptides are usually destroyed instantly by stomach acid. I mean, they don't stand a chance. To get around this, they co-formulated semaglutide with an absorption enhancer called SNAC. When the pill hits your stomach, SNAC acts like a microscopic shield. It temporarily raises the local pH, basically neutralizing the stomach acid right around the pill, protecting the fragile peptide, and then physically promoting its absorption directly through the stomach wall and into your bloodstream. Honestly, it's a massive pharmaceutical achievement.
Okay, so once this highly engineered molecule is circulating in your blood, what does it actually do? Well, it acts on 3 distinct organs. The first is the pancreas. Semaglutide enhances insulin secretion, but brilliantly, it does so in a glucose-dependent manner. This means it only prompts your pancreas to release insulin when your blood sugar is actually elevated. At the same time, it suppresses glucagon, which stops your liver from dumping even more sugar into your blood. Because it only kicks in when sugar is high, it drastically reduces the risk of severe, dangerous low blood sugar. And that is a huge upgrade from older diabetes medications. The second organ it acts on is the stomach. Semaglutide essentially puts the brakes on your entire digestive system. It causes something called delayed gastric emptying. By physically slowing down how fast food leaves your stomach and enters your intestines, nutrient absorption is smoothed out. This prevents those massive blood sugar spikes after a meal.
Plus, this also creates a prolonged physical sensation of being full. But, as we'll see in a minute, this exact mechanism is also responsible for the drug's most notorious side effects. The third organ it acts on, and I gotta say this is the most crucial one for our narrative today, is the brain. Semaglutide actually crosses into the central nervous system, specifically targeting the hypothalamus and the brainstem. These are the ancient, deep regions of our brain that control appetite and feeding behaviors. By binding to receptors up there, the drug physically rewires the neuronal pathways associated with hunger. It cranks up the signals that tell you you're full, and it effectively quiets what patients constantly describe as food noise. You know those obsessive, intrusive thoughts about eating and nonstop cravings?
Of course, dramatically altering the body's digestive and neurological systems definitely comes with biological costs. On the more common side, patients frequently experience nausea, vomiting, diarrhea, and abdominal pain. And almost all of these are directly caused by that delayed gastric emptying we just talked about, because, well, food is literally sitting in the stomach for a lot longer. However, the FDA also mandates severe clinical warnings for some rare but very real risks. There's a potential risk of thyroid C-cell tumors, mostly based on rodent studies, as well as risks for gallbladder disorders, acute kidney injury, typically resulting from severe dehydration, and pancreatitis.
But here is where the story takes a fascinating, completely unexpected twist. As millions of people began taking these drugs for diabetes and weight loss, doctors started hearing these bizarre anecdotal reports. Patients weren't just losing their cravings for a midnight snack, they were suddenly losing their interest in alcohol, in nicotine, and even in other addictive substances. People who had been heavy drinkers for decades suddenly found a glass of wine totally unappealing. The medication wasn't just quieting food noise anymore, it actually seemed to be silencing drug noise. And this brilliantly illustrates the power of big data to investigate these sorts of wild anecdotes. Researchers at Washington University School of Medicine in St. Louis decided to see if these stories actually held up at scale. So, they analyzed the electronic health records of over 600,000 U.S. veterans with type 2 diabetes. They split them into groups, those taking a GLP-1 medication like semaglutide, and those taking entirely different diabetes drugs. Then they tracked them over 3 whole years.
The data from this study is, quite frankly, staggering. Let's look at patients who did not have a pre-existing addiction. For them, taking a GLP-1 medication significantly prevented new substance use disorders from forming across the board when compared to other medications. The risk of developing an opioid use disorder dropped by 25%. For cocaine, the risk dropped by 20%. For alcohol, it dropped by 18%. This medication was somehow exerting a protective effect across entirely different classes of highly addictive substances. It's just mind-blowing.
But what about patients who were already battling the demon of addiction? Well, the results here are literally life-saving. For veterans with pre-existing substance use disorders, taking a GLP-1 was tied to a 30% reduction in emergency department visits, a 40% reduction in overdoses, and an absolutely incredible 50% reduction in drug-related deaths. Just think about that. Half as many people died from their addictions when treated with this class of medication compared to standard diabetes care.
So the crucial point is captured perfectly by Dr. Ziad Al-Ali, the senior author of the study. He noted that in addiction medicine, treatments usually only target one specific thing, right? Like a nicotine patch for smoking. But that doesn't do anything for alcohol. But semaglutide works uniformly across all major substances because it isn't targeting the specific drug. It's targeting the fundamental biology of craving itself within the brain's reward centers. As he puts it, moving beyond food noise to drug noise, GLP-1s are quieting the roar of addiction. We started by looking at a molecule that was engineered to survive the human stomach and bloodstream, just to help the pancreas manage sugar. And we end staring into the deep, complex neurobiology of human desire, reward, and addiction. It leaves us with a profound question. If a single molecular tweak can simultaneously treat diabetes, cause historic weight loss, and quiet the overwhelming roar of drug addiction, what other shared biological pathways are hiding in plain sight? What else is our brain waiting for us to unlock? Thank you so much for joining me on this explainer, and I absolutely cannot wait to explore the next scientific breakthrough with you.